Hi, and welcome back to Book Club. I'm Dr. Andrew Duckleby, and we're in Thermodynamics. Moran and Shaipro. This is chapter 2, and this is where we start getting into some of the more fun parts of thermodynamics, ideas behind energy and work and heat, which is ultimately what thermodynamics means, right? It's sort of, driving motion with heat. And so, something you should have been familiar with in your physics courses, you would have had, kinetic energy. That should be a very familiar concept, and we might define that as, say, 1/2 mv squared, mass being an object. If I'm throwing this pen at some velocity v, it would pick up some kinetic energy. So hopefully that's a reminder of your kind of early physics days. We also would have talked about potential energy. And that might be that same mass times gravity times height, right? So if I lift this pen from here to here, I've increased its kinetic energy or potential energy. And then if I wanted to convert it, I could just drop the pen and it would go from that potential energy down to the kinetic energy and hit the ground, right? Drag will take a little bit away from it, but it's kind of some basic key concepts. And then when we started talking about thermodynamics, right, a lot of times we're talking about just the transferring of energy between systems. And so there is going to be an internal energy, which we'll just use U for the internal energy. Because you may have some chemical reaction that's happening, right? This might be a car engine, and I've taken air, I've mixed fuel in it, I'm going to burn the fuel. And that might be the point and change behind that kinetic energy. It was actually starting from this sort of chemical energy, and then the difference in the chemical energy because some reaction occurred, reaction being burned. And so really that's kind of where it starts, but then where it gets interesting is ultimately when, well, I want to take a look at work. And work is just the integral of force along some direction. And so, if I was to be pushing a brick on a road, I've got to drag the brick on the road and I'm pushing it and it's work, right? So however far I pushed that brick, it's going to pick up work. And then power is another one that we almost defined. And power would be just the kind of force times the velocity. So if same sort of thing, if I'm pushing that brick and I've got it up to some speed and I'm just holding that speed, right? A power would be representative of how much energy per time is it taking to kind of keep the brick in the same speed. And if we looked at, as just a basic example of this, think about a car. So, if you've got some car here, some really awesome car, there's my perfect looking car, and it's going forward at some velocity. Well, we might want to talk about how much power is it taking, how much work is it taking. And, as you may have learned in another class in fluid dynamics where we'll talk about it, there's a drag force, and that drag force is usually modeled as something called dynamic pressure. We'll explain that here in a second, times the area times some drag coefficient. And so, people would use wind tunnel measurements or computer simulations to figure out the drag coefficient. But this would be what it looks like. Well, the dynamic pressure is really just 1/2 the air density and then the velocity squared. And so if the car's going this way, it's actually slamming into the air. It's not that the air is coming at it. And so then you would have area times drag. And so if that's your drag, then you might take a look at it pretty quickly and see that, well, the power is going something like V cubed. So power, and you can think about like horsepower. And so, it's no surprising that when you are, at a faster speed, your engine, right, it's a lot more power you're going through, okay? A lot more fuel that you're going through to generate that power. And so, that's hopefully not surprising. And, if you've ever been running low on gas, right, what do? Well, you would actually slow down. You want to slow down because your fuel burn is less at slower speeds. That's why, right? And it really makes a difference, right? It absolutely makes a difference. But to link back to the word work, well, what if, I am trying to go so far, right? And so ultimately, if you're trying to drive your car and you have to make it to the gas station, yes, your power goes like V cubed, but if you're trying to get to some distance R, then it's actually that force, that drag force times, so the work is the drag force times that distance R. And so you would see that actually goes like V squared, for example. So, yes, if you're running out of gas in your car, do slow down, it will help you go further, right? It will help you go further because that picks up like a velocity squared term. And so, when we start talking about work, though, we really want to talk about this from a thermodynamic process. And we're going to get into what is really, I'll kind of draw this piston again. So if we have some piston, and our system is the dotted lines, and then there's our piston, right? And during the compression process, and you fuel and you add it, things like that. Well, ultimately, the change in work, so again, like kind of more on the calculus side, change in work is that the force times the change in length, right? The length being, going up. And so, that's going to look like pressure, because this has got some sort of pressure, times the area. Well, that's just the area of this piston, right, times the length. Or if you do that, if you go some height here, total height here, well, then you might actually say that you could see that it's going to be this sort of change in volume. So delta work is equal to P times some delta V. And so, we may actually be able to draw that on a graph and say, here's P, and there's my volume. And, you may have some nonlinear curve, but this is just an equation, and it's a differential, right? It's set up in a differential form. So to get the total work, you would integrate it. Well, integrating is just area under the curve, right? So a little bit back to like that math in calculus, it's just the language. It's just the way to talk about like, well, I don't have a straight line here. What am I actually looking at? Oh, the work is the area under the curve under this system, right? So that would be one way to look at it. Now, another really important concept in thermodynamics is equilibrium. So this piston is going up and down, right? And so there's this concept where we can do a lot of analysis if the system is in equilibrium. Nothing's changing. Well, that's almost never true of any system we're looking at. However, really, what we might add to this term is a word called quasi-equilibrium, because it all just depends on timescales. So imagine your car engine is just going nuts. Let's say you're sitting around at 6,000 RPM, and so that's rotations per minute. Well, 6,000 RPM, that's 100 rotations per second. That still feels very fast, right? And so honestly, that means one cycle every 10 milliseconds is one cycle. So this thing is going up and down in one cycle. That still may feel very fast to you. But now let's talk about the combustion process. Well, if I fill this and I hit the ignition, boom, the combustion process might completely happen in 10 microseconds, right? This is 10 to the minus 6 seconds. And so combustion is 1,000 times faster than the whole process of this engine going up and down. And so, that's why a lot of times when we're doing basic analysis, you might think of this piston coming up to the very top, top dead center, and then magically the heat appears. And that's not bad. Now, if you were digging into this, and 6,000 RPM might be a little faster than what you're doing. So if you're an engineer and working on car engines and things like that, like, okay, it may not be instantaneous. You may have to do a little bit more work and say that combustion is happening over, you might turn it into crank angles, happening over a couple of degrees of crank angle. That's not just happening instantaneously. But for the most part, we can take a look at that and it's happening instantaneously. And then every crank angle, every slight change in this piston going downward, we actually can look at each one of those states and understand what is the pressure, what is the temperature, what's the density, because the change of all of that, right? The temperature in the system is going to be fairly uniform. Why? Because the air molecules are banging around. Does it mean it's always uniform? No, but a lot of times in these early kind of first order estimates, you can go a long way by sort of assuming equilibrium and kind of going through it. I've been gosh, undergrad for me was a long, long time ago. And I've been an engineer throughout my career in many different aspects, from rocket sciences to manufacturing to high-speed vehicles. Really what you're doing, there's absolute power in being able to, frame at first principles, like what's going on. There's power to understand, like what's the next level down. And honestly, part of the success when you're trying to say build a business and go fast and do really cool things, a lot of it comes down to choosing the right level of tool or choosing the right level of analysis. And I'll just say it this way: I've found in many cases you have, say, an engineer that might take 2 days doing a deep calculation on a thing, when the answer was like what they could have done in 2 hours with some simplifications was probably plenty enough. So we're going to find that a lot through the course of almost everything we talk about, because the world is full of complexity. And in the end, you just kind of go, you just got to go fly it, you just got to go test it, you just got to go do. But it's worth understanding the layers behind all of this. And so within this piston, the last couple of concepts to talk about is, we talked about like adding adding the fuel and hitting the spark. Well, that's heat. So we could think about that as heat, usually known as Q, coming into the system. And so heat has a couple different ways we want to think about it. Really, heat has heat transfer. There's conduction. And you can think there of some rod of length L, and you've put, use orange, you've put the end of this rod into a fire, and you're holding it over here, and what's the thermal conductivity? And so yes, there'll be some heat that is going to transfer down that rod based on the temperature of your hand here and the temperature of the fire over here. So that's conduction. Yes, that's going to happen. You can also have radiation, and you can think of either the sun, or you can think back to this fire. It's radiating it away. So this fire actually has photons spraying away from it, and that heat transfer is going to look something like emissivity, Stefan's volts constant. There's an area, but it goes like T to the fourth. So the temperature of the fourth is radiation, and we'll look at that a little bit more. Stefan Boltzmann constant is really, it's a unit conversion thing. That's the easiest way to think of it. I have T and Kelvin, if you will, which is one of the units, depending on what my area is. This just gets this in terms of the right units for heat. And then you have convection, right? And convection is simply, I'll draw it here as just a boundary layer, if you will, and there's some velocity of a gas or a liquid going on this boundary layer, and maybe this wall is hotter than the fluid. And so it's actually, you're picking up heat from the wall. It's really, at the minuscule level, it's conduction, but that convection is going to take that cold thing and stir it and toss it, and if there's turbulence, it's going to make it, enhance it even more. And so, the world of thermodynamics is actually kind of looking at these systems, looking at them in quasi-equilibrium. You're going to have work coming out of the system, right? So how do you calculate the work area under the curve? You're going to have heat coming into the system or maybe out of the system. And so that's a lot of what these systems are going to look like. And in the end, we may talk about a cycle. So the cycle could be, this piston going up and down. A cycle could be many different things. And so in the end, you may talk about an efficiency. Let's say you have some engine, right? I'm going to have the efficiency, which is, what's the thing I'm trying to get out of my car engine? Well, I'm trying to get work out of the car engine. Well, what did I pay for it? Well, actually, I paid for it by whatever that Qn is. Now, if you isolate this and you do all these different things, we could actually also figure out that the work would be the Q in minus the Q out, right? The amount that in was the combustion from the products, and the out was whatever we had to put out. And so this is actually the Q in. And so that would be an example of how we would consider the word efficiency. We'll come back to like refrigerators, where what you're actually doing is what you want is the heat out, and you're paying for it is the work in. But we'll come back to that. And so we'll take a look at these cycles, right? Whether it's an engine cycle or different things like that. They're the whole process that lets us You know, take thermodynamics, right? Take fluids and heat and mass transfer and use it for our purposes, whether through a chemical reaction in an engine that gives you, work, horsepower, whether it's, the power coming from your wall through a pump and refrigeration system to pull heat out of your fridge. We'll get through all of that. And it's all sort of this relationship between internal energy, potential energy, kinetic energy, work, and heat. So we'll see you next time.